because it's almost, because if I...
Good afternoon, everyone. For those of you who don't recognize me, I'm Susan Hockfield, the president of MIT, and I am really delighted to welcome you to today's colloquium. I want to thank Ernie Moniz and his colleagues at the MIT Energy Initiative for organizing this event, and I want to welcome some of the members of the External Advisory Board who are here for our full day of meetings tomorrow. Some of you are new to the board, others of you are returning, and it's I anticipate it will be a great day, although I can't promise you. That's up to Ernie. But I view this afternoon's colloquium as a little bit of an appetizer for the day tomorrow. And I especially want to thank Dr. Arun Majumdar for coming to visit with us from Washington. He is the director of the Advanced Projects Research Administration Energy, and he has agreed once again to come to MIT and share his insights. The topic of his talk is the challenge of energy innovation, and that challenge could not be more central to our work here at MIT. And we're all very eager to learn more about the critically important role of ARPA-E as champion, as supporter, and as accelerator of the innovation process. Now, before he assumed the role of inaugural director of ARPA-E, Dr. Majumdar served as the Associate Laboratory Director for Energy and Environment at the Lawrence Berkeley National Lab. He also, I think, concurrently was a professor of mechanical engineering and material science and engineering at Berkeley. He has great credentials. He's a pioneering research scientist in his own right, as evidenced by his membership in the National Academy of Engineering. He served as an advisor on nanotechnology to the President's Council of Advisors on Science and Technology. He has advised startup companies and venture capital firms in Silicon Valley. He brings everything that's needed to the task that ARPA-E has set out. And I would say it's fortunate for all of us and for our nation to have him in his position. ARPA-E came to life about 1 year ago with the goal of accelerating the transformation of the energy landscape. To do that by bridging the gap in our innovation system between idea and device, the gap between innovation and application. And ARPA-E has already demonstrated itself to be a powerful ally in closing that gap. ARPA-E's vision and starting momentum remind us in the scientific community, at least those of us who are old enough to remember, of the early days of DARPA in its most dynamic phase, when it was busy setting the seeds for the IT revolution. Like DARPA, ARPA-E seeks to provide vital support for revolutionary technologies, and ARPA-E is also very active in delivering those solutions to the marketplace in time to make a difference. But I would offer the thought that ARPA-E faces a far more daunting challenge than DARPA did. Because when DARPA brought us the IT revolution, it didn't contemplate displacing an incumbent industry. And I would say it wasn't really working against a fast approaching deadline. But transforming our energy system by mid-century will require navigating tough economics and politics to launch new technologies into a well-established energy landscape by mid-century. This is a daunting assignment. That said, Dr. Majumdar and ARPA-E have enunciated a mission with inspiring clarity. They're committed to finding and funding the white space in energy research. There's opportunities that have been previously missed, but have the potential to be transformational, and that could be on the road to commercialization within 5 years. Now, that's the kind of clarity and urgency that today's energy challenge demands. Dr. Majumdar was last here in December, shortly after taking on his new role, and since then, ARPA-E has decisively demonstrated its commitment to accelerating high-risk, high-reward research, and I'm delighted that a healthy share of that research springs from MIT. I won't bore you with examples, but many of you in the audience have been the beneficiaries of some of ARPA-E's intelligent investments. Here at MIT, we believe ARPA-E can play a critically important role in speeding the transition of ideas into action, and we are committed to working with Dr. Majumdar and his team on this critical assignment. It's an assignment of the gravest importance for the nation and the world, and we have declared ourselves allies in this cause. So please join me in welcoming Dr. Majumdar back to campus.
Great. Well, thank you very much indeed, Professor Hockfield. And it's delightful to be back here. And, you know, what was sort of the most interesting part was I spent about 1.5 hours with the students. And I was just relating that. And I said, you know, let's not talk about just MIT. Let's talk about the country. What do we need? And boy, I got a grilling from them. It was like taking a qualifying exam. So, but we had a great chat. So let me talk. What I'm going to do is to give you first a little bit of a historic perspective. This is not just about ARPA-E, but broader. And a little bit of bad news that I recently heard. And then I'll share the good news, the optimism that I feel looking at all the ideas that are being thrown at us. And so let me start first about what the problem is. This is the population density of the world. And we are over here in this corner, high population density, but you can see this is the United States, high population density in Europe, pockets of Africa, large population densities out here. The energy problem can be correlated with the population issue. We are going to double the population. We are about 6.5 billion people. It's going to be around 12 billion people by the end of the century. And about 99% of that growth, it's going to be in the developing nations. So that is a huge issue. And the other aspect is that where are they today? Well, this is the lighting is not quite appropriate, but you can see this is a picture of the Earth from space at night and stitched together. And this is the energy, sort of a reflection of the energy use. You have pockets of, you can actually tell where the cities are, you know, Boston somewhere over here. The other way. Great, thank you. And this is Europe. You can actually see the Nile. And you can see Japan, a bit of China and India, et cetera. When you overlay the two, you find that energy use and population are not correlated. You have really bright lights out here, but there are many parts of the world where the people have not yet turned on the lights. And if they turn on the lights the way we have done in the past, I think we have a problem, we have a challenge. And the real challenge that we have is how do we enable people out here to turn on the right kind of lights and keep our lights on and maybe make them brighter without the impact on our resources and environment that we would otherwise have if business was usual. The other way of putting this is the following. We are going to live in a resource and carbon constrained world. It's not just carbon constrained, but resource constrained as well. This is the carbon dioxide emissions per capita per year. And here is GDP per capita, which is sort of correlated to income level. And United States is over here. This is the global average, about 5 tons of CO2 per year per person. And we are number 1. And we're competing with Australia. And here is per capita, of course. Here's China, India, Brazil, Mexico, all the developing economies. And these economies are growing fast. And so the question is, this is today, or a few years ago, where do these countries go? And you can see some of the countries, France, because of nuclear, they have maintained a low carbon emissions, Japan because of efficiencies, et cetera. Well, if you ask the question where these countries ought to be going, what path should we take? For the United States, I hope this is the only path we take. I hope we don't go any other way. Maybe in a higher GDP per capita, but in terms of carbon emissions, hopefully lower. But for countries over here, there are multiple paths. I mean, there's a sort of a scaling relation out here, sort of, a trend. Well, business as usual, they will be taking this path. Because if nothing changes, they'll be taking that path. But what we're seeing now from the developing economies, China, India, et cetera, they realize that it is not just for carbon emissions, it is for the local environment and as a prosperity of the future of their population that they would rather take this line. And the question is, if they are to take this line, many of the things in this pathway do not exist today. And this gap between the red and the green and this transition are huge challenges. This is the whole Titanic shifting. But this is also an opportunity, because this is a business opportunity. So whoever grabs it, it's up for grabs. And we need to grab it, frankly. The question is, are we ready to grab this? Well, let me give you a few wake-up calls on this one. This is where the bad news comes, so pardon me for that. This is lithium-ion battery manufacturing volumes in 2009, last year, before the Recovery Act. And this number is a little forgiving for the United States. It's actually less than 1% last year. And with the Recovery Act investment, hopefully this will climb to around 15, 20%. Nevertheless, let's just take last year, 2009. And in the same year, we gave the highest award from the Department of Energy, the Fermi Award, to John Goodenough for inventing the cathode of the lithium-ion battery. It's absolutely ironic that this happened in the same year. And while this is a global market, and while the United States will not have 100% of the market share in manufacturing volume, but less than 1% is staggering. It's unacceptable. There are other examples, solar cells. We manufacture less than 8% of the photovoltaic solar cells. And in the mid-90s, we had more than 40% market share. So you can give many, many examples. Another wake-up call. We certainly import 60% of our oil, some of it from places that are not that friendly to us. But the other part is I was involved in Secretary Chu's science team in stopping the oil spill, along with Alex Slocum from MIT. And Alex and I can give you lots of stories. And I'm sure he, and certainly I, lost some sleep over this several nights because we did not know which way it was going to go. And it certainly turned out fine, but for a while we were not sure. And there are lots of stress analysis, et cetera, that Alex can give you that we were not sure whether it's actually going to work. Nevertheless, this is a risk. And the more we go, we have to understand this risk. So if you look at this whole scenario, you find that innovation in the energy side is really the core of our national security, of our economic security, and our environmental security. This is the DNA of our nation. And we have to get this right. And if we don't, we won't be able to grab that opportunity that I talked about. So where are we? Well, we heard about creation of ARPA-E. It came out of a report from the National Academies, which was led by Norm Augustine, the former chairman and CEO of Lockheed Martin, called Rising Above the Gathering Storm. It was a large report covering many areas like K through 12 education, STEM education, et cetera. But there was a proposal that you need a DARPA-like organization to take the risk. And if you recall the history of DARPA, it was created in 1958 in response to the launch of Sputnik, when it was felt that the US was losing its technological lead to the Soviets. They said, we need to leapfrog. And it was, let's take some risks and create technologies that do not exist today. So this, in the same vein, ARPA-E was created. And it was launched through authorization in America Competes Act in the previous administration, and then launched with money in the Recovery Act last year. Now, it turns out that the same committee met. This was issued in 2006. The report came out. And they came, so just to give you a few quotes of this, I won't bore you with the details. They basically said innovation, largely from advance in science and engineering, is absolutely the key. But what is also key is while 4% of the nation's workforce is composed of scientists and engineers, this group disproportionately creates jobs for the other 96%. So MIT graduates, this is really important. The burden is on your shoulders and the science and engineering community. But they also, this year, they met together again, the same committee, and came up with this other report called Rising Above the Gathering Storm Revisited. And the storm is rapidly approaching category 5. Okay? So I want to read out a few excerpts from this. And this is what was kind of a wake-up call, certainly to me. So I won't read the details of this, but a few lines. The unanimous view of the committee members is that our nation's outlook has worsened. And that is primarily, while progress has been made by launching, for example, launching ARPA-E, so we got highlighted, but the growth of the national debt over this period from $8 trillion to $13 trillion. And that is a big deal. The other part was, and again, I won't give you the details, but the fact is the other nations have made markedly progressed towards this clean energy economy, and that is, which they should. Other nations should be, and we should be welcoming that. It says that. But our our nation's relative ability to compete is going down. It's a relative ability. Again, innovation is the key to the process. And fortunately, this nation has in the past demonstrated considerable prowess in this regard. So it is there in our DNA, but it just hasn't been dormant. It's been a dormant gene for a while. Let's get it activated in the energy area. A few other factoids and quotes. Amongst the manufacturers of photovoltaics, wind turbines, and advanced batteries, the top 10 global firms by market cap include 2, 1, and 1 US firms, respectively. If you said the same thing about information technology, there would be a hue and cry. But that's where we are in. And then the other one is US spends more on potato chips than energy R&D, and more on dog food R&D than the R&D in the electrical power sector. Now, I have a dog, I have a yellow lab. I'm not sure he really cares for dog food R&D. He would eat anything. But nevertheless, that's what he'd do. All right? A few other quotes, amusing quotes, but a little worrisome. This is Tom Friedman. In today's integrated and digitized global market, where knowledge and innovation tools are so widely distributed, whatever can be done will be done. The only question is, will it be done by you or to you? Again, this is the opportunity. We have to grab it. And this one is also interesting. The greatest long-term threat to United States national security is not terrorists wielding a nuclear or biological weapon, but the erosion of America's place as a world leader in science and technology. This is from the Department of Defense. This is what I like. Gentlemen, we have run out of money. It's time to start thinking. Sir Ernest Rutherford. Okay, that's where we are. The question is, can we grab it? Grab this opportunity, and can we start thinking? So has the world faced such a challenge before? This is, I mean, stepping out from our local national thing, has the world faced such a challenge before? And absolutely yes, and science and engineering came to the rescue. Perhaps the most important one of the last century, I'll just highlight it, is this one. There was in 1898 calling upon science to save the world from starvation. William Crookes, the president of the British Association for the Advancement of Science, he's a physicist. He said that there was not enough nutrition in the soil in Europe to be able to grow food. The population was slowly increasing because of better water quality, et cetera. And there's not enough food. So there was a mad rush to get fertilizers from South America. First, Guano Islands. This hill is basically Guano Island that's been basically dug up. Guano, as you know, is bird poop, but it has a lot of nutrition, and that was a fertilizer, and they ran out of guano. And then, fortunately, by a stroke of luck, Chile had Chilean saltpeter, and that's what was used as fertilizers also for growing food in Europe and the United States, also for making explosives in the Civil War. So Crookes did some calculations that if you take the whole capacity of saltpeter, it would still not be enough. We'll run out of it. And there was a mad rush, Europe sending ships out there, and there were battles between fights, wars between Peru, Bolivia, and Chile around that time, late 1800s. And I said, we got to start thinking now. And he put up a challenge for the chemist. In 10 years, Fritz Haber, the chemist, discovered a catalyst that would combine atmospheric nitrogen with hydrogen to form ammonia, which was a precursor for fertilizers. And the catalyst was uranium and osmium. This is pre-nuclear. And in 5 years, this is the combination of science and engineering, which is unique. In 5 years, chemical engineer Carl Bosch developed a process to mass produce ammonia to make fertilizer using high-pressure chemistry, got invented at this time. And the Haber-Bosch process, of course, is basically what saved the world. There were 2 sets of Nobel Prizes, a fantastic book called The Alchemy of Air. If you haven't read it, it's worth reading, because it tells you the geopolitical environment at that time, the business environment, and the science and engineering in that context. It's fantastic. What is important is that it touched humanity like none other. Here's the population of the world and the year, and it changed the trajectory. And most of us in this room would not be here if it was not for this invention. So this was an example of how science and technology changed the ballgame. It's a game changer. Other game changers was Norman Borlaug. The Green Revolution dwarfed strain of wheat. Land use remained stable, or remained constant. Food production, grain production went up. He got the Nobel Peace Prize. And this grain production in Mexico and the Indian subcontinent was basically, essentially avoided famine. And most likely, I would not be here if it was not for that. Polio vaccination, another example. Salk and many others created this vaccine. It was, again, a game changer. Science and engineering came to the rescue. And that 4% basically disproportionately created the life for the other 96%. So we are in this situation right now, as Secretary Chu says, necessity is the mother of all invention. The problem that we have today is the mother of all necessities. And so the question is, can we step our game up? So the way I look at it is the following. If you look at the pace of and scale of innovations that we need now for this particular problem, the scale that we have, look at all the game changes of the 20th century, starting from, as I said, artificial fertilizers, green revolution, polio vaccination, antibiotics, airplanes, electrification, nuclear energy. Look how many have come from the United States, and all the way down to the internet. Okay? Most of the kids know internet today, but they may not know the artificial fertilizer, Haber-Bosch process, et cetera. But look at that happening in 100 years. And imagine that happening in the next 20 years. Because that next 20 years is absolutely key, has to be the most inventive time of our history. And it has to be done in the people like this in this room, in the science and engineering community. Aligned with policy, aligned with finance, and aligned with education. So that is what is needed. So we ask the question, what is that list that is the next 20 years? What is that list? Well, I think everyone should create a list like this. And I think we should all put that together. Here are some thoughts on that. Here is that potential list. I don't know how the future will be, but here is some imagination of what the future could be. Solar electricity generation at a cost lower than that producing fossil fuels. And let me put a number, $1 a watt fully installed electricity. If you can do that, it'll scale without subsidies. You don't need subsidy, you don't need policy then. Real-time optimization, security, extremely important. Storage for grid with a two-way dispatchable electric power. If you could do that, that would be great. And can we do it in a business way? Carbon capture and utilization at a net cost lower than its market price so that there's a business associated with it. Someone can make money out of it. That's the way to scale. Car batteries, I'm going to talk a little bit about the car batteries, which are 3 times higher energy density, 4 times lower cost. And many of the people out here are thinking very, very hard creatively about this. Transportation fuels from sunlight at a cost lower than petroleum. If you could do that, then there's a way to shift over. So economics is a key factor. So the question is, can we develop the technology to change the economics? Reduction in energy consumption in buildings can be reduced by 50 to 80%. Policy, very important in this case because there's some market inefficiencies out here. Lower cost desalination of water. And of course, I have to put nuclear. Low cost, safe nuclear energy. At the end of the day, on the supply side, it's sunlight and nuclear. And can we do this in a cost-effective way? ARPA-E's mission. So it is in this framework that I think that the fathers of ARPA-E, the people who wrote the report, conceived of this and Congress then enacted, and there's a clear mission. The mission is for long-term, high-risk technological barriers. We need to overcome them through technologies. This is not policy. We are supposed to do technology. There are 2 mission statements. One is to enhance economic and energy security of the United States, so the development of technologies. 3 sub-missions, reduction of imports of energy, reduction of emissions, as well as improvement of energy efficiency across the whole sector. And number 2 is to ensure that the United States maintains its technological lead in the developing and deploying advanced energy technology. This is the mission. So we ask the question, what is an ARPA-E project? The first thing is that, does it address the mission? What is an ARPA-E project? It is high impact on the mission areas. But we are also looking at the technological barriers and interpreting that in the following way. We are looking at new technologies, devices, and prototype systems that do not exist today in the market. If they're already existing and if you're improving it, that's great. If that's our insurance policy, ought to be done. We should be investing in lithium-ion batteries. That's there in the market. But there are other parts of DOE that do that. We will not touch it. But that are too risky for the private sector for investment. That are too risky today. And finally, if successful, could make today's technologies obsolete. That means if you're creating a battery, would rather have the competition to the lithium-ion battery from inside the United States than from outside. Because someone else is going to do it. We might as well be first. And there's an advantage of being first. We've always go back from the airplane to nuclear to the transistor, et cetera. We have taken the lead. The only one that we did not was space, and we created DARPA. And we need to sort of get that. Let's be the first one. Let's take the risk. Could have large commercial impact and could produce new learning curves and new markets. And that, we ask the question, if it is successful, will the private sector pick it up? That means, will it create value to someone? Because if it does, then someone would pick it up. And finally, getting the best-in-class people. And combining science and engineering. Sometimes the barriers are artificial. Combining them in one team so that the feedback is there inside in real time. That means scientists understand what the systems are like and where the target ought to be, so they're not going other areas. And engineers understand what science could potentially do to change the system itself. That feedback has to be there together. And getting the intellectual horsepower, the best computer scientists, the best biologists, et cetera, to focus on energy R&D. And that is what we're looking. This is what we are looking for in ARPA-E teams and projects, et cetera. Give you a few examples. Here is a technology, Agravita, is a startup company actually here in Boston, looking at to reduce the cost of cellulosic biofuels by eliminating the process of enzyme creation. So most of the cost, a lot of the cost, is in these enzymes, cocktail of enzymes called cellulase, exocellulase, endocellulase, to break down cellulose into sugar molecules, which get fed into microbes to produce fuels. That's very expensive. So what they have done is taken the genes that are used for these enzymes, to produce the enzymes, put them in the plant itself, and the plant produces enzymes, but they're blocked, or there's something called an intine, which they're not active. They're inactive enzymes. But then, after a while, when the plant grows, you activate them, and they chew down the plant from the inside. That's the idea. I have to explain this to people who are non-technical. I said, that's like putting the cow inside the plant. And that's what they're trying. We don't know whether it's going to work, but it's worth a shot. Well, here itself in MIT, Don Sadoway, makes these batteries, which are amazing, making aluminum, taking aluminum manufacturing in an electrochemical way and turning that into a battery. Another one, which is wind turbines, where using the principles of fluid mechanics and jet engines in trying to use some very nifty vortex dynamics to beat something called the Betz limit, which is the efficiency limit, and actually reducing the cost. Now, it so happens that all these projects are related to MIT. And one would say, oh, Arun is trying to push, only present the MIT stuff. I presented this in California. I presented it anywhere in the world. These are just good ideas. And so there's a whole bunch of ideas that came out in the first round. What we have done in the second round is to now focus. The first round was open. Any ideas, throw it at us. And of course, as some of you know, we got about almost 4,000 proposals to deal with, and there were only 3 people. The first one was from here, Dave Danielson, who created the Energy Club. Nevertheless, so these are now, I'll just describe some of the programs that we created. This one is on transportation batteries. And what I'm plotting out here on the vertical axis is the energy density out here. And these are the different kinds of batteries. And this bar out here is the theoretical limit of different kinds of batteries. So lithium-ion batteries of today, it's about 350 to 400 watt-hour per kilogram. And this is the effective energy density of fuels in an internal combustion engine. It's about 3,000. So it's about a factor of 10 away. There are other batteries, zinc air, which is hard to make it rechargeable, lithium sulfur, lithium air, and a whole bunch of others. And there was practically no investment in this area. The Japanese government were investing about $60 million a year, and the private sector probably 10 times that. And there were, battery manufacturing is something which has been done for decades, hasn't quite changed. So we created a program called BEAST, Batteries for Electrical Energy Storage. It's an acronym, and we have acronyms for a variety of things. To put a marker out there, 400 watt-hour per kilogram, which is about 2 to 2.5 times higher than today, and 4 times lower cost. So that multiplier in performance cost ratio is a factor of 10 or so, which if you've read Andy Grove's book, Only the Paranoid Survive, you will know that if a 10x factor comes in, things go obsolete. And that's the idea out here, and new manufacturing techniques. And out of that came a whole bunch of things. MIT flow battery from Yet-Ming Chang, magnesium-ion battery from Gert Cedar, and a bunch of others, zinc air, rechargeable battery, lithium sulfur, 2 kinds of lithium air batteries, and new manufacturing techniques, applied materials, which is a large-scale manufacturing for semiconductors, but not in the battery space. A123, as you all know, is a battery company, got together and said, let's do large-scale manufacturing of batteries. So this is a program which we're really excited about. Carbon capture. Today's amine-based carbon capture is expensive. And it's, for coal-fired power plants, about $70, $80 a ton of CO2, whereas the market price in Europe, at least, is $30 a ton of CO2. So someone wants to start a business in carbon capture, they start with a loss of about $50 a ton of CO2. It's a non-starter. So we said, amines have a certain learning curve. Are there other approaches to carbon capture which have not been tried? And out of that came some very interesting ideas. Here's an example of a reagent based on water, and you expose it to carbon dioxide, and the carbon dioxide creates a reaction where you can extract the carbon dioxide as a solid. So you don't have to heat it to get the carbon dioxide out. You don't have to heat the water, which, as you know, heat capacity is very high. And this potential cost is about $25 to $30 a ton of CO2. So we said, OK, let's take the European price. Can we go lower? Because then you can start business. And this one is from GE. And this is a large company. And they found it serendipitously. It's not quite there in a business thing. They said, OK, let's see if this actually works out. This is another program, electrofuels. And here is taking on the biofuels and creating a competition, internal competition. Most of sunlight to fuel today is biofuels using the photosynthetic route. And the photosynthetic route is you take photosynthesis and you take carbon dioxide and you fix carbon dioxide, and either using in biomass or in algae, using algae. And this whole route is about a 1% efficient. That means from photons to chemical bonds is about 1% efficient. There are other routes in biology that are up to 90% efficient, which had not even been used to create fuels. And so we created this program. And the idea is that you generalize the concept of biofuels. You can take any reductant, not just sunlight and excited electrons. It could be hydrogen sulfide from waste from oil and natural gas. There's a lot of hydrogen sulfide. People don't know what to do with it. Or hydrogen, or ammonia, or oxidation of iron, or just direct current. Then this is photosynthetic route, which is Calvin-Benson cycle. But there are many other cycles for fixing carbon dioxide that have really not been used. And of course, you can generate a variety of fuels. So we said, this is like a mix and match. It's a Lego set. You can take this reductant out here, this organism out here, this cycle out there, and you get a fuel. So, and this is taking on really the biofuels, the current biofuels approach, and creating a parallel approach. We don't know which one's going to win, but let's give it a shot. These are some of the new programs that we created. I'll describe a few. Energy storage. So if you take a wind ramp that is coming in from Oregon, let's say in Bonneville Power, there's a whole front that comes, and the wind energy goes up, and people are trying to balance it. But if you look at the gap between the supply and demand, you find that you need about 1 gigawatt of power in about an hour. So this is like a nuclear power plant has to come up in an hour. And that is really difficult to manage. And that's why we only use about 20 to 30% of our capacity, and otherwise it's all wasted. So storage, but it has to be done at a cost which is equivalent to pumped hydro. So that is something that this program looks at, is how do you bring the cost of other storage techniques, not just batteries, but other things, to a cost which is less than $100 a kilowatt hour. Because if it is less than $100 a kilowatt hour, it will scale not just in the United States, but anywhere else in the world. Cooling technology, I'll describe a little bit of that. Power electronics, this is what Rajiv Ram from here, who is an IPA in ARPA-E, has created. Let me just describe a little bit. There's one project, which is a transformer. Today's transformer, if you look at a substation, we buy all our transformers from China, all our transformers. And if you look at, it's about 10,000, almost 10,000 pounds in size. It's done at 60 hertz or a little bit higher. And so this is a new technology based on silicon carbide. I won't go into the details. But if this thing works, and if you go to higher frequency, 50 kilohertz of modulation, using in a substation between transmission and distribution, you can reduce the size to 100 pounds, and it'll be based on semiconductor-based switches. And so which will be fax compatible, and you can make an intelligent grid based on this. So this is, and there are a whole variety of other projects on this. On the cooling side, again, I won't go into the details. This is the two kinds of loads, humidity load and a thermal load. And usually you have 90 degrees Fahrenheit, 90% humidity, and you want to get it cold. And there are two ways of doing it. One is refrigeration and then reheat. So you cool the air, get all the moisture out, and then heat it again, which is a total waste in energy. Or you go the desiccant way, where you basically heat up. You grab the moisture, the thing heats up, and then you cool the heck out of it. And the question is, can we go down this way? And no one has really tried this, because this will be, if you can do it, it'll be energy efficient. And we said, how far are we from the theoretical limit? So we did an internal calculation, a few of us did that. And we said that this is the primary energy use in kilojoules per kilogram of air. That is, this is primary energy use. And this is the coefficient of performance of vapor compression. And this is the theoretical limit. And today, most of the current systems are a factor of 10 away. So we said, if you are to do cooling, instead of creating a program saying, make a better compressor or better desiccant, we said, forget it. Let's just put the target out here and let people innovate. And what we found was just some amazing ideas. This is an idea which actually goes down this way. This program, by the way, is called Beat It. So let me just throw this. The Beat It is, you have to, I haven't created that. Beat It is building energy efficiency through innovative thermal devices. So we have to be creative about this. And we get this on a Friday evening beer bar, and that's what we do. So we put a target and said, beat it. And what people came up with are some membranes to extract out moisture without taking the air and oxygen and nitrogen. And they feel that they can potentially beat the target by 50%. So this is, you give an engineer or a scientist a target, they want to beat it. And that's exactly what they're trying to do. A completely new thermodynamic cycle based on reverse osmosis, which is used for cleaning water or desalinating water, used for refrigeration and air conditioning. Because water, if you think about it, is the best refrigerant. The problem is that we don't have a compressor, and this gets around it. And they feel that they can potentially beat the beat it target by another 50%. So this is great. We'll see. And this is just a small project. So who have we funded out of all this? Well, it turns out that this number is, universities about 40%, small business about 40%, just the number of projects. And this is a large business, this is a national lab, this is a not-for-profit. These are actual dollars breakup, and that's where it has gone. It's just a little report. We have on our website where the project leads are. It's totally out there. And here are the project leads, and here are the leads and the subs. We're trying to fill the United States and get everyone going. But obviously, there are some pockets of innovation out there already existing. But we're trying hard to get everyone involved in this because it really needs the whole nation to participate. Where are we going next? And these are some of the workshops that or one of them we organized, we're planning to organize right now. $1 a watt fully installed. We had a workshop in August. Natural gas production. I'm really thankful for MIT to take the lead on natural gas report, which I think was wonderfully written. With natural gas production, we have found a lot of natural gas, shale gas. There are some environmental issues with that, in terms of water contamination, et cetera. We got to deal with it. Then storage and efficient use. Can we use natural gas in a judicious, economic way for a transportation system? Because if that works out, we could reduce our imports of oil. Grid security, reliability, capacity, control, optimization, whatever, all the words behind SMART, those are the words. Integrated energy systems for distributed generation and use. Because we are looking at vectors the following. If the grid goes two-way, and I hope partly it will go two-way, and if the cost of distributed generation comes down, at some point you need integration. You need to look at the whole architecture and say, this needs some integration, and that is missing today. And in the DOE silos, you have air conditioning program, a combined heat and power program out there, this program, and we need to integrate that, and that's what we're trying to do. Heat storage, by the way, this is 90% of our energy is in heat, and we don't know how to store it very well. For long periods, we don't know how to do that, so we're going to look at that. Rare earth minerals for clean energy. And if you look at what happened, this recent dispute between China and Japan over the fish trawler, rare earths were brought up as a political pressure. And this is something that was noticed, and there are many reports that are coming out. We said we better look at this quickly, and we're going to have a workshop on this because many of our clean energy, like magnets or phosphorus, et cetera, depend on rare earth, and we need to either recycle it, reuse it, or avoid it in some way if you can, and that's what we're going to look at. So, and the other one is student competition. I'm going to very briefly talk about it. We need energy literacy in the United States. If you think about it, our kids know more about megabits than megawatts. People know more about the horsepower of their cars than the horsepower of their homes. And we don't know where the energy goes in our homes and our buildings. So this is a competition, and we are going to engage the energy clubs as mentors for the high school kids to really measure, report, compete. There'll be a competition, compete, and see if you can get the energy consumption down in a substantial way. Because if you wait for utilities to put smart meters and then somehow, it's not going to happen very quickly. And speed is of essence out here. A little bit of the team. It's really important. We're 1 year old. How we set up this team and how the organization develops, we have spent actually a lot of time on this, thinking about it. I'm not sure we got it all right, but we're trying to. And first thing is the people in the program team. These are some of the, I'm really proud of these people. Ravi Prasher left Intel, gave up all his stock options and everything, joined ARPA-E. None of these people needed a job. They're doing it to serve. So this is the program team, endowed professor in chemistry and biochemistry, Duke, Dave Danielson, you all know him, he's a graduate from here. Mark Johnson has MIT connections, Mark Hartney as well. Rajiv is a faculty out here, and we're growing. There are a few other people, I don't have the pictures, all of them. So they're just joining now. And so then there's a commercialization team. And their job is to look out for our projects that we have funded and help them go to the next level. Whether if it's a small company, where do they get the next round of funding? Even if they don't succeed, they are part of the ecosystem and they need to be supported. So that's their goal. And what is the landscape? If someone wants to start a business, who are in that landscape and what's the channel? And that's their job out here. Operations team, and I'm going to talk a little bit. Not enough people talk about operations and the speed, et cetera, and then the outreach. The operations team is extremely important. They're all behind the scenes. They don't get enough credit, but they do all the hard work in getting things done quickly. And if you ever visit ARPA-E, and I welcome you to do that, we don't have security issues and all that. It's a different building. Just walk in. We have a walk-in policy. And we all sit, the lawyers, the scientists, engineers, the contracting officers, we all sit in one space. And it's very cozy. It's not much space. And that culture of having the same sense of mission, we all go out for lunch and we debate and we go out for beer on Friday evenings. That is something I think is understated, absolutely important for an organization when it starts off. So here is some yesterday's feedback that we got. And I was not in Washington. Someone sent an email. And this is on the contracting. I just want to highlight them. ARPA is allowing our company to expand into something that is outside the main product line. our project, this is a DOD contractor. Our project will have positive DOD implications long term. Okay, that's great. Being selected by ARPA-E has allowed us to make contact with investors and other partners. Very thankful. This is their commercialization team helping them out. The next one, really liked how our ARPA-E's expectations are, how high ARPA-E's expectations are. Excited to work with a world-class scientist. This is our technical team now. And the final one is, could not believe how fast contracting was done, did not think it was possible, very thankful and impressed. And he also said most of the time he goes to the Hill to complain about contracting being slow. This is the first time he'll go do the opposite. And so this is now the contracting. So every part of the team is now working together to help these guys out. And there's some other comments, I won't spare you the details. We created an ARPA-E Fellows program. This is not part of a statute. So in many ways, we violated the statute. But Congress liked it enough that they're putting it in the reauthorization. And this is, I felt when I went from Berkeley to ARPA-E to the Department of Energy, that the best thing that has happened in the United States is the people out here, the students out here, formed an energy club. And that's happening not just in MIT, and happening across the nation, where the students in science, engineering, public policy, business, law, they've broken down the boundaries and formed an energy club over pizza and a few drinks, right? But they want to change the world. And this is the hope I have for the United States, because that kind of passion I have not seen anywhere in the world. And so we said we need to leverage and empower these guys, because it's their future. It's not my future, it's their future. So we created this program called the Fellows Program. This is not a program to give you a fellowship to do research in your lab. And there are programs for that. We said we want the best and the brightest in the government, because we need parity between what is there in the government and what is there outside. We need the best and the brightest to spend a couple of years maximum and create a think tank. These are scientists, engineers, technical entrepreneurs, to create a think tank to look at that energy diagram, the spaghetti chart, supply, demand, et cetera, and see how you can rewire this and think differently. They won't have any management duties, any responsibilities, but this is a think tank, help the program directors create a workshop. And this is not just a think tank who will write a report. Yes, reports are very important, but this could be with muscle behind it, because we could put dollars behind this, because if it's a really good idea. So that's 80% of the job. And the next 20% of the job, and these guys are working really, like 70 hours a week, the 20% of the job is to get the next generation involved. And that's where the student competition, et cetera, will come in. We had this year, we said, we need to talk about this in an open way and get all the communities engaged. So one of the things that we did was this ARPA-E Energy Innovation Summit. So let's just open it up. We had 2 months to prepare. 1,700 people showed up. And we brought in the scientists and engineers, the entrepreneurs, other DOE offices, federal agencies, the investment community, the venture capital, large, Wall Street, et cetera, state and region clean tech, incubators, White House, Congress, policymakers, we got them all. So let's come together. And then we showcased the ARPA-E technologies that we funded, and also brought in the people we could not fund, because it is really an ecosystem that we need to build. And what happened was that in the showcase, there were deals, we heard later on, deals, financial deals got made with many of the technology showcase people. We thought it was a good thing. We heard some great feedback from people. We decided to do it again. And we are doing it again. So this is for people to make a note. It's going to be February 28th to March 2nd, 2011, next year in Washington, DC. And this time, last time we had 37 projects to showcase, and about 50 of the ones could not fund. This time we have 120 projects to showcase and several hundred that we could not fund. We're going to bring them in. It's going to be fantastic. So I hope you join us. Let me end my talk with a quote. And this quote was made in a different time for a very different reason, but it's absolutely perfect for this time in our history. It's by Martin Luther King. We are now faced with the fact, my friends, that tomorrow is today. We're confronted with the fierce urgency of now. In this unfolding conundrum of life and history, there is such a thing as being too late. Thank you very much. Sure, I'll be happy to answer questions.
We'll take some questions. Questions? If you could use a microphone, it would be preferable. It's not too hard.
So, did I understand right that ARPA-E largely, if not exclusively, funds projects that people write proposals for? But if I look at some of the items on your list of game changers, take the transistor. Penicillin was not on your list, but that's another. These didn't come from people having a specific, well-planned project. It came from very creative people with a creative record who are working in the field. And even today, as you know, I don't work on energy, but in fields that I work in, even today, the most creative and exciting things often come out of individuals who are working in the field and have won some lottery that allows them to think without constraints. So in this field, would it be a good idea to put part of your budget to fund creative people rather than creative projects only?
So, Arup is one of my best friends, and he had to ask me the hardest question. No, absolutely. I think, look, at the end of the day, when I said that we need to grow the ecosystem, many of our projects will fail, but they will be part of that ecosystem. The teams have to be built up, and people need to be supported, okay? Now, whether they're supported like a Pioneer Award in NIH or a Career Award in NSF, or there are, from Office of Science, there are Young Investigator Awards as well now in the DOE. How we do that is something that we need to figure out. We haven't. We've been around for 1 year. We had to obligate our Recovery Act money, and we are waiting for our budget for next year and the years after that, hopefully. But this has not escaped, as the famous words, it has not escaped our attention. And at the end of the day, we need to fund innovators. But I believe in this case, it is really important to get the teams right. It's not individuals. Individuals are important, but I think the teaming, 1 + 1 can be greater than 2 in that case.
When one looks at ARPA in its origins, and when one looks in the environment that you're playing in, both policy and in a commercial environment, how good of a job do you all do in benchmarking what's going on, R&D at Siemens, at GE, et cetera? How do you create situational awareness so that you're not creating unnecessary redundancies as part of the ecosystem you're evolving?
Oh, great question. Our program directors are required, first of all, to go out and see what is going around. Then we have a workshop. All programs are created out of workshops. All workshops don't lead to programs, but programs have to be created workshops. We bring in the community of the experts. And so the programs that I talked about had a workshop behind it. And then we ask the community what's out there, okay? Now, you may say that, okay, in an open workshop, people may not have discussed openly the proprietary stuff. We said, and we improvised on that. So after the workshop ends, typically around 5:30 or so, and it's in a hotel, we go to the bar of the hotel, and then we have 20-minute sessions of individual people talking to me and my program director on their proprietary ideas. And this session goes on till 11:30 midnight. Probably the most exciting session for me. But that's how we are getting to know what's out there.
But this is sort of a trick follow-up question then to that. Your biofuel funding notwithstanding, and I mean alcohol is the biofuel in this sense. If you're
better drunk than used for driving.
If you're going out around that, the tension that I see is that, as you rightly pointed in your opening slides, there's interesting work going on in Japan, in China, and of course India. How do you strike a balance between?
We actually keep we keep our workshops international.
Okay.
We invite from people anywhere. Let's get the best people together, and if they can be part of teams, that's fine. We need the best minds to solve the problem. There's a U.S. focus aspect of it, right? But frankly, this is a global problem, and a lot of people have come. Other countries, when I've traveled around, have said that, can we create an ARPA-E? I said, absolutely, you should be creating an ARPA-E, and we will help you do that in other nations.
you're a technical person. I'm on.
Yeah.
There was yet another depressing article in either the Times or the Journal this morning about how innovative companies in Silicon Valley can't get their new, innovative, exciting products to scale in manufacturing because every time they're about to, the Chinese, and various pejorative sort of statements were made after that, reduce the cost of manufacturing conventional technologies by some large fraction. You scared us at the beginning of your talk, or depressed us maybe, by talking about how there's a dearth of lithium-ion battery manufacturing in this country. And then you went on to encourage us to continue to innovate, and make more lithium batteries and more non-manufacturable solar technologies. Is there anything going on at ARPA-E in manufacturing innovation, or are there linked programs in DOE that help to bridge the gap?
Right. So, great point. You know, in all my testimonies to Congress and my private conversations, this is something I've raised as if there's anything that keeps me awake at night, it's not the fact that we can't innovate. We can. We have the best science and engineering infrastructure as of today in the United States. The question is, how do we scale those innovations in the United States? And that worries me, frankly. And we need to get sort of post-R&D things right. If there's a demonstration, the demonstration should be geared to make it market compatible and fund it adequately with private sector involvement. That, I'm not sure we have it quite done yet. I think there's a huge, and I've said this in my testimonies, that, and I'm not the only one who've said this, there are many others who have said it, is the biggest buyer. We need to create a market for clean energy. The biggest buyer of energy is the US government. The question is, can we use that purchasing power? They're buying energy anyway. Can we use part of that purchasing power to enable clean energy technologies to get a foothold and scale in both volume and reduce the cost so that eventually, at the end, they become market compatible? And that's something that we need to take, I feel we need to take really seriously to be globally competitive. Because otherwise, it is, if business as usual, we will innovate and things will scale elsewhere. And that worries me.
If I can just follow up a bit on that, Arun. It seems to me that, I don't mean only in energy, but in technologies in general, we have, for a long time, had a major advantage of a huge domestic market,
Yes.
a dominant market. We're not going to have that market in the energy space, even if the federal government does buy some stuff.
Right.
How does that jive with?
Well, I mean, we need to get the market, you know, as I said, most of the market could be overseas because that's where the growth is, right? You'll see the economies are growing in China and India, et cetera. And we need to think globally. But if the scaling can happen out here, my worry is that if we don't scale, then the R&D labs will go abroad. That's what they are, right? There you go. So I think we need to, if there's some, if you keep at least the early stage manufacturing out here and sell it in the growing economies, it's a global market. That's what we ought to be doing. There's a beautiful article in, I believe it was Wall Street Journal or somewhere, about how Germany has done it. They are actually, actually not taking the innovations and scaling in China. They're selling the products in China. And that's the way it ought to be done. And we need to sort of look at that and see whether it can be done properly in the United States. So
Feed-in tariff will do.
Right. That's a policy issue, yeah.
If you look at why the lifetime of a battery lasts longer when it's used with low power, it's not just because the power draw is low, it's because you can trade volume for surface area and the chemistries become more reversible. So by putting together energy generation with energy use, you can actually get a solution that would not have been possible before. So one of the big problems that I see in the world today is there's a whole bunch of people who say, oh, the power budget is 15 terawatts. Given that it's 15 terawatts, let's find all these fuels and energy sources to meet it. Then there are a whole bunch of people who say, well, let's reduce 15 terawatts to 1.5 terawatts, and we don't worry about the fuels. But the actual solution is the feedback loop between energy use and energy generation. There may be a 2 terawatt solution that is possible through an energy source that only improves twice, and then because it's tied to an energy use load that impedance matches to it, the combined solution actually is the only solution that will work in the feedback loop, not trying to get the battery to be 100 times more power efficient or saying the use of it. So a good example is the Cheetah. The Cheetah is 22 times more power efficient than a car, and it goes from 0 to 68 miles an hour in 3 seconds. And the reason the Cheetah does this is it's got an 18,000 joule per gram fuel inside its body, the glucose, but it's using it in a very clever way by adiabatically recycling energy in its backbone, figuring out that mostly it should be jumping rather than running. And all these tricks, which actually give the Cheetah the combined solution that's made it, the amazing animal that it is. And the same thing with the lithium-ion battery tied to the load. So my question is, what is ARPA-E doing to bring these 2 people together? Because I would love to be one of these people who brings these 2 people together, but I talk to people who are interested in the 15 terawatt problem. I talk to people who are savvy about reducing the power, but I never find anybody who thinks about it as a system and says the solution is not in the fuel, it's not in the load, it's in the combined fuel and the load. And that's where the optimum is.
So the whole architecture, actually, if you look at today's supply and demand, the supply is generally centralized by utilities, and the use is all distributed. And those are the 2 extremes that we have. It's a question that you're asking, if I reframe it, is there a solution in between where you have distributed generation and use? And in fact, you could really reduce the primary energy consumption by, if you do combined cooling, heating, and power. But we don't have that today. And there's a lot has to be said about how the grid is structured today, and whether there's a value in terms of just dollar value in doing combined heat and power and distributed generation. So I agree with you. That's one of the workshop topics, by the way, of integrated systems for really looking at the supply and demand in an integrated way and not in a disaggregated way. Okay.
I think I can throw a flower. Given the magnitude of the energy problem, why such little emphasis on the implementation of nuclear power with advanced light water reactors?
Well, as you know, Secretary Chu and the President is both really keen on getting nuclear up and going, or jump-starting, if you may. And today, if you look at what has happened over the last 2 years, really, it's about 1.5, 2 years, is to really get these things out into the, into really getting these power plants going using loan guarantees. It has not been easy, even that. And so today, what we are trying to do is to get these, and this is not ARPA-E, I'm talking on wearing the DOE hat, is to get these loan guarantees out, to get the nuclear plants going. There's a lot of focus on small modular reactors, as you all, you know this, you all know this better than I do. And there's some value in that. And that's sort of the next thing that would be coming in Gen 3, Gen 3 Plus, et cetera. Yeah, I agree. As I said, I wish we could go nuclear in a massive way, but there's an inertia in the system that needs to change.
Okay, one question there, and then we're going to bring it to a close.
Sure.
I'm wondering, ARPA-E is not a policy agency, I know, but how important is a carbon tax to hitting the goals that ARPA-E has for energy?
Look, I think there's not just a carbon tax, let's say carbon price, whether it's cap and trade or tax or whatever that may be. It would be very helpful. Okay, there's no question about it. It would be very helpful. But the reality is we don't have it today. And whether we have it tomorrow or not, we can't wait for that. Okay? So my challenge to the scientific community, the technical community, don't wait for it. Go for your technologies now. And given the environment, reduce the cost so that you may not need it. And if it comes on board, that's icing in the cake. Because if you can get these technologies to be competitive in this environment, difficult environment, without the policies aligned with it, you'll be globally competitive. And so that's the challenge that we have. That's a reality. I can't say anything whether it will happen or not. I don't know. Right.
So after such an inspiring talk, I hate to raise another downer, but the year before last, when Secretary Shultz was here for the External Advisory Board, he gave a talk that said the past must not be prelude, decrying the roller coaster in funding of energy. And I think we'd all agree that the level of funding for energy has been pathetically low and not the sort of funding that would lead to the kind of innovation and transformation that we all wish to see. And it's fabulous, money for, ARPA-E. This is all really exciting. We've got a lot of people working on important projects, but what is your level of confidence that we are not on another roller coaster cycle of funding, and that the federal funding that supports these critically important early technologies can be continued now that the nation seems to have been in deficit reduction mania? When,
Right.
The politics of it just become very hard, and I think, we're all, of course, worried about what will happen to research budgets as people are elected to Congress on a mission to do it as a primary purpose to reduce the deficit.
Right. Well, I mean, that's a great question. I don't think I have the answers to all that, but I can say that I'm sure you've come across this report by the American Energy Innovation Council. And this is formed of some thought leaders in this nation, Norm Augustine, Bill Gates, John Doerr, Chad Holliday, and several others. And they have recommended, as you know, that this problem, and many of them, as you know, are not from the energy field, but they feel that this is important enough that energy should have a budget of about $15 billion or $16 billion a year. Today, it's about $4 or $5 billion a year, so it's 3 times that. And also, they've recommended that ARPA-E should have a much bigger budget, and I won't argue with that. But it needs to be framed. Let me also put another reference point. And this is, we inquired into that. I mean, the council said that ARPA-E should have a budget of $1 billion. And so if you look at DARPA and go back in history and ask the question, what was DARPA's budget? If it was that big a deal, what was DARPA's budget? And it started in 1958, but its first appropriated budget was 1962. For 4 years, they scrounged around money and supported it. In 1962, the appropriate budget was $246 million in 1962 dollars. And one could do the math and see where it is today. So that was then. So we need to sort of, as a nation, I guess, look at the importance of energy and environment and see whether it can be done. But at the end of the day, the budget is between the president and Congress. And we are in a tough situation in terms of deficit. So, yeah.
Maybe I will take the prerogative of asking one last question.
Sure.
And make it more lowbrow.
Okay.
But following on that, I mean, I think ARPA-E is off to a very promising start.
Thank you for your support. Yeah.
In both process and in the project being supported. The funding is very low. But there is another couple of billion in what I call the traditional applied energy offices. They do not seem to operate in the mode that you have just described. That would suggest one of 2 things. Why don't you spend their money, or why don't you help them spend their money better?
No. I wouldn't go there. I thought that was a lowbrow. That's a hot soup comment. Let me put it this way. We have taken it upon ourselves in ARPA-E to coordinate very, very closely with Office of Science and the Applied Energy offices. We invented a new word for this called InReach. Okay? And the idea is that we need to make this a win-win proposition. And if some other office in DOE needs help, we will help them. So if you go back and see how our workshops were held, not all, but most of the workshops were joint workshops. And so as to be able to see, like for example, the buildings work. We had a buildings workshop that I organized. I wore a program director hat and said, okay, I'm going to organize it with people in EERE, Energy Efficiency Renewable Energy Office. And out of that workshop came the idea of how to separate out what the buildings hub is going to be doing. And since I'd spent some time in the buildings area, I actually wrote the technical side of the buildings hub. It's a different office, but I wrote it for them. And also the ARPA-E program called Beat It. So that we leverage our funding, or leverage our teams in a way that it's a win-win thing. So we're trying to do that as much as possible. We are doing the same thing with Office of Science, and to see that, their success is when some of the scientific concepts that were developed or discoveries that were made actually get into a rapid technology development in ARPA-E. That'll be their success. And so that's the idea. And if we are successful, and one of our teams needs the next round of funding, we go to fossil energy or EERE, and they pick it up. And so that handoff is something that we're trying to create. And there are other things, I won't go into the details out here, that there are a panel of people that we have created who are advisors to ARPA-E from across DOE, and that they coordinate, including the undersecretaries, et cetera. So we are trying. Thank you. Thank you very much.
Thank you. Thank you. It's the roller coaster.